Welcome back, everybody. So in this last video I want to mention some properties of ordinals and the class of all ordinals. I go through them verbally, but I like you guys to go and check all the details, make sure you understand why each of these is true, using uh, paper and pen and reading like I was reading last week in the textbook. Just make sure every little detail is clear. Okay, so here's a theorem about ordinals. It says that whenever you have ordinals alpha, beta, and gamma, bunch of properties. First two, I guess, in the textbook they are in that order. Well, this one essentially is just because we know that an ordinal is a transitive set, right? We prove all ordinals that so you're an ordinal if and only if you're transitive and the belongs relation is well ordered. So ordinals are transitive, therefore this is the case. Actually, any member of an ordinal must be an ordinal. Why is that? Well, we have that if you have that X belongs to an ordinal alpha, then alpha is transitive. So you get that X is a subset of alpha. So the ordering relation as it is transitive, the ordering relation on X is the same as the ordering relation on alpha. I mean, the belongs relation on X is the same as the belongs relation on alpha, right? Because if you have that Y belongs to Z, and these are two elements of X, then Y belongs to Z as element. They are also elements of Y because alpha is transitive, so the same ordering you have there. And also, if you are a member of a transitive set, you must be transitive too. Because if Z belongs to Y that belongs to X, since we know that X belongs to alpha, then we know that Y belongs to alpha, then we know that Z belongs to alpha, and now we know that among the elements of alpha, any two elements are, this alpha is well ordered by the belongs relation, so you must have either Z belongs to X or X belongs to Z, but you couldn't have X belongs to Z because then X will belong to itself by transitivity inside alpha. So you must have that Z belongs to X. So that's that part. Alpha doesn't belong to alpha, then this is because alpha is a transitive, the image of this epsilon function, and we already showed that in that case you never belong to yourself. Also because we know the belongs relation in alpha is well ordering, a strict well ordering, so nothing inside belongs to itself. Exactly one of the following holds. Alpha belongs, whenever you have two ordinals, alpha and beta, either alpha belongs to beta, or alpha equals beta, or beta equals alpha. This is an important one, okay? So whenever you have two ordinals, either they are equal or one belongs to the other. And the reason for this is that we know from the previous theorem that either alpha with the ordering epsilon alpha is isomorphic to beta with the ordering epsilon alpha because they are well ordering, or alpha epsilon alpha is isomorphic to the segment of some B inside beta epsilon alpha for B inside beta, or we know that the segment of some A inside alpha is isomorphic to beta, right, for A in alpha. But what is the segment of B according to the epsilon relation? Well, it's everything that's below B, so it's everything that in this case belongs to B because we are using epsilon relation, right? So being below means belonging to, that's the relation we're using here. So everything that belongs to B, what's everything that belongs to B? Well, that's B, right? And what is everything that belongs to A? Well, in this case is A, right? So in this case we get that alpha is actually the same as B, right? I mean, they are isomorphic as well ordering, so they must be equal. So we get alpha equals B because they are both epsilon images of the same thing, which belongs to beta. And in this other case, we get that beta is equal to the A that belongs to alpha. To draw this in a different way, what's going on here is that if you have an ordinal alpha and you have an initial segment A of all the things, and you have things below A, then this thing is exactly A, right? Each element is equal to the set of all the previous ones, right? And when we have ordinals, if we have that beta is isomorphic to this initial segment, then beta actually is equal to the initial segment because they are both epsilon images. And if you're equal, then you must be equal to this A, which belongs to alpha, right? So in the case of ordinals, being an initial segment is the same as belonging. Cool. Or in other words, yeah, so the segment of all the things below A in A is actually the same as A that belongs to A. That's what I'm saying. Cool. Last, every non-empty set of ordinals has a least element. Well, this is because if you have a set of ordinals S, and it has some ordinal inside, let's call it alpha, then you do S intersection alpha, then we have a subset of alpha, right? And then that one has a least element because it's a subset of alpha. But now every ordinal in S that is below that, well, everything in S, now S doesn't have anything below that least element because if it was below that least element, it would be in alpha, so it would be in S intersection alpha, right? So essentially this is a kind of an initial segment of S, so the least element of S intersection alpha is the same as the least element of S. Again, work out the details. As a corollary, we get the Burali-Forti paradox. I mean, this was originally stated as a paradox before ZFC was developed. People were working on ordinals a bit below before ZFC was developed, right at the turn of the century. And this is one of the paradoxes. There is no set of all ordinals. If you put all ordinals in a set, we get a contradiction. That's what it's saying. And what's the reason? Well, if you put all ordinals in a set, by our previous properties, this set will be an ordinal itself, right? Because it's linearly ordered by belongs, is transitive, is linear, and it will be well ordered. Every subset will have a least element, right? So if the class of all well orderings is kind of well ordered, so if it was a set itself, it will be an ordinal itself. But then you will have that this ordinal belongs to itself, because we're talking about the class of all ordinals. If it has an ordinal, it belongs to itself, but that cannot be the case for ordinals. So we get a contradiction right away that the set of all ordinals, well, the class of all ordinals cannot be a set. Okay, it's larger than any set, essentially. We get a bunch of other properties here just to build some ordinals. Any transitive set of ordinals is itself an ordinal, well, because it's transitive and because every subset has a least element, so it belongs is and it's linearly ordered and well founded. So if you're a transitive set of ordinals, you're transitive and belongs is well founded, well ordered. So you must be an epsilon image, so you must be an ordinal. Empty set of 0, or the empty set, is an ordinal number. We saw that. It's the epsilon image of the empty well ordering. Whenever you have an alpha plus, an ordinal alpha plus is also an ordinal. You guys remember what this guy was. This is a set alpha union alpha. And essentially this is what you get by, if you have the well ordering alpha, putting one element on top bigger than all the other ones. You have to show this guy is transitive. Well, you have to take an element from it and see that it's included. It's not that hard. And you have to show that belongs relation is well ordered, but you're adding one thing on top, so that shouldn't be hard. If A is a set of ordinals, then the union of all the elements of A is also an ordinal. Well, this is because all the ordinals are transitive, so every element of an ordinal is also an ordinal. So the union of A will be a set of ordinals. It will be transitive too, because each of these guys is transitive. So if you take the union of all these transitive sets, you get a transitive set. And if you get a transitive set of ordinals, it must be an ordinal. So the union of a whole class of ordinals is itself an ordinal. And actually, this union is the supremum of all the ordinals in the class. In the terms of this ordering that we have among ordinals, you're going to get that this guy is equal to the supremum of all the ordinals in the class A. Alright, so that's it for this week. All these properties are a bit delicate to look at, so please spend some time trying to understand all the little details behind these proofs, because that's the only way you can get used to working with such an abstract object like ordinals. Alright, see you guys next week.